This is project 2 by Logan Lawrence. I'm going to be doing the second part. So from A, B, C, and D, I will be plotting the velocity profile at 25, 50, and 75 centimeters on the same graph. And then getting the boundary layers for each, tabulating those, and comparing to the theoretical values. I'll be plotting the wall shear stress and skin friction coefficient along the flat plate and comparing that with theoretical values. Then I'll also be getting the drag coefficient and comparing that with the theoretical. Let's go ahead and begin. So first I have open my Excel. I'm going to go to Discord where my partner has sent over the XY files for each that I need, which is velocity, skin friction, and wall shear stress. Go ahead and download those. There they are. And because they aren't exactly in the format that I want, I'm just going to copy them manually rather than import them. Let's do wall shear stress first. Do wall shear stress. We'll do skin friction. Velocity at 0.25, 0.5, and 0.75. Let's actually do position, and then value. Just to keep coordinated there. There we go, wall shear stress. Grab skin friction. And then velocity. Now we're just going to sort these really quick because they aren't in the right order when exported from Fluent. There we go. Now we're going to build our theoretical values, or at least the table for them out. Let's do it right here. Theoretical. We want our Reynolds number, our boundary layer, our skin friction, our stress, and our coefficient of drag. And we want that just from 0 to 1. Start at 0.01, we'll go up to 1. There we go. Let's actually move this over. Well, let's just move down a little bit so we have a little bit of space for our variables. Here. Now, for air, we have rho, mu, L, and then U infinity. Density is going to be 1.2. Mu for this assignment is 1.8 e negative 5. Our length is 100 centimeters or 0.1 meters. U infinity is 2. And let's also just define here that our boundary, the end of our boundary layer, we'll just call that bound U, is going to be 1.98, which is 99% of our U infinity. Now we can go and start filling these out. For Reynolds number, we just have rho times L, or not L, sorry. This is our L here. L times U infinity over mu. And we want all of these to stay the same except for our length, which will be changing. So let's go and use some dollar signs to do that. That is just rho UL, or rho UD over mu, 1.32, 0.1. We used the wrong U. We want T9. There we go. Drag that out for all these values. Sweet. And now for boundary layer, let's pick this aside so we can start referencing the assignment. Boundary layer is just going to be 5x over the square root of RE, which we just calculated. Ready? Equals 5 times Rx, which is just going to be our distance here. So 5 times this over square root RE. We don't need any dollar signs here since everything will be iterating. Drag that out. Great. Skin friction, 0.664 over square root RE equals 0.664 over square root RE. Drag that out. Tau, or our shear stress, is a bit longer, equals to 0.332 times, that is mu. We should probably put that in parentheses. Mu to the 1/2 times rho to the 1/2. Yeah, I think we'll probably be fine without them actually. Just keep the same format throughout. To the 1/2 times u to the 3/2 over x to the 1/2. Do a quick look through just to make sure because this is a bit longer. Let's see, what are we doing wrong here that's not valuing? 0.2 times. Hmm. 2/2. Times S. Maybe we'll just throw this in parentheses, perhaps? No? Let's start just closing things off a bit. Let's just remake it. So we are doing good. Equals 0.3, maybe 0.332 times mu to the 1/2. What if we do? Oh, we're calling mu. That would was that how we were doing it last time? Okay, yeah, that'll do it. Alright. Alright, let's drag that out. Zero 0.332 times mu to the 1/2. You know, I think we might be over describing this. Let's drop some of these off. .332. All right, drag that out. Will that change anything? No, those all look the same. Well, some of these are errored. Okay, that'll do it. Now we just need to caret off all these, or sorry, $sign off all these ones that we're going to be keeping the same. Just like that. I'll drag this back out. All right, and that's better. Now for CD, quite easy. That is just 1.328 over square root of Reynolds. So that's going to be our total Reynolds number. So we'll take that from the end here. Since that is 1. 3.64 e to the -3. I actually want all of these to be a bit more precise. So we're going to take scientific notation off of these. Where would I find that? There it is. We're just going to do, I think, just text. 3637. Yeah, I think this is enough precision. So now we have our modeled and theoretical values. Now we can go ahead and start grabbing our boundary layers. I kind of want to move these, but I'm just going to leave them there. So we want to check our boundary layer, which just for reference is at 1.98 per second, which is again 99% of our U infinity. Now we want to find our boundary layer for ANSYS and our theoretical for, or sorry, at 0.25, 0.5, and 0.75. Let's just be 75, 50, and 25. Make more sense. So we'll come here. We're looking for 1.98. Or rather, crossing over 1.98. So it'd be here. 0.8. Here. We're taking the first value. 0.98. Here. All right, and for theoretical, we're looking for 25. 50. And 75. So there's our comparison of our boundary layers at the 3 locations for ANSYS and theoretical. That is our excuse me, boundary layer thickness values. And then it wants us to plot them. Okay, so we have, let's see, we still need to plot the velocity profile for those 3. It's going to be in the same graph. Let's just tabulate these really quick. Plot all 3 velocity profiles, same graph. Get the boundary layer thickness values using the velocity profile from fluent and pair. We've already done that. They're here. Plot the wall shear stress and skin friction coefficient along the flat plate using fluent compared with theoretical, and then get the drag coefficient for the flat plate using fluent compared with theoretical. We actually do have the theoretical CD. We'll just put that here, and we'll do CD ANSYS theoretical. And then my partner already got that, which was here. You can see him getting that in his video. 00435. I don't like the way that looks. Okay, just 0.00435. So there's our comparison of the data, ANSYS theoretical for CD and boundary layers. Now let's go ahead and plot all 3 velocity profiles on a graph. We're just going to want 3 of these guys. I'm going to go ahead and make this full screen since we don't need to look at that for now. Let's see about this size looks good. Let's make it fit this a bit nicer. There. I want 3 of these. Can I just copy these? No? Okay, well, we will just make 2 more. If it will let me. There we go. And we want 1 more. Sweet. So this is going to be velocity in this one, skin friction and shear in these other 2. Make them all about the same size. There we go. There we go. All right, let's take this, select data. We're going to just name this 25 for our x values. Actually, want to start here. Get rid of that. We want this 25 here, x values for our y. We want these 50. X values here, y values here, and then we're getting 75. plot those. They look good. Kind of low resolution, but that's the standard plot that we do want. I think we made it so big. If we shrink that down, it looks a bit nicer. But I don't like it big. And we'll do that title now. Velocity profile. We want our legend and our axis titles. Just a second. And position. Looks good. Kind of. This is a bit. I think it'll be fine. We'll just. That'll decide which is which. All right. Now I'll do shear stress. Simulated. There it is. And then we want shear stress. Theoretical. Looks good. Our bounds are a bit big, so I think I'll change those. If I can remember how to find them. This one was in here. There we go. We're just gonna go to 0.2 for this. Yeah, that way we can see clearly how it diverges. They are very close though. And yeah, that looks fine. Now we'll go ahead and title it. Sim versus theoretical. And then this is our skin friction. Rear looks good. Again, the bounds need to change a little bit. I think 0.1 looks good for that. We really just want to see the difference, which is in between the two. That looks good. Bring up the legend, axis titles. All right, there's our 3 graphs. Let's see if what else we need. No, go away. All right, so responsible for uploading a link showing data analysis and graph table generation in Excel. Export to Excel, and we did the theoretical calculations. Contours, that is the fluent work. We've plotted the velocity profile on the same graph. And then we got boundary layer thickness values using the velocity profile obtained from fluent, compared them with theoretical ones. Then we plotted the wall shear stress. You can show it while we're talking about it. So that was velocity. Wall shear stress is here. Or theoretical there. Get the drag coefficient for the flat plate using fluent, compare with theoretical ones. Yeah. Or this is, one second, this is still big. I want this at 0.1. Actually, 0.05. Yeah, it's better. Great. As you can see, they're all pretty close. There is some divergence, but for the theoretical that was actually computed, it's quite close. Same with skin friction. And then for CD, there is a slight margin of error. And same with the boundary layer calculations. But all in all, they're very close. Which shows ANSYS and theoretical calculations are very similar, I guess. But yeah, this will be submitted alongside the video. Thank you.